In this video, we will talk about how to solve constrained optimization problems using substitution. So, optimization is just a word that means to maximize or minimize depending on what the question is asking for. Okay, so it's an overarching term that we use to describe questions in which we want to find a max or find a min. So let's look at an example. So in this example, we actually saw most of this before. There's just one extra piece. This question says a cruise line sells two kinds of tickets to passengers, luxury and economy class. Economy passengers pay $2,000 for the cruise, while luxury passengers pay $3,500. The cost in hundreds of dollars of taking X economy passengers and Y luxury passengers is given by this function c of x comma y. So up until this point, this scenario we saw in an example in section 8.3, our previous section on maxes and mins. The additional part now is we're also going to suppose that they sell 340 tickets total. So there's this extra condition. So this part is new to this specific example. And just like before, the question asked me to find the combination of passengers that will maximize the profit. Okay, so I want to introduce a little bit of terminology to discuss questions like this, where we want to optimize something, find the max or find the min of something. So I'm going to call something the objective. And the objective is just a term we will use to refer to the quantity that we want to either maximize or minimize. So let's make that parentheses bigger. Quantity that we want to maximize or minimize. So in this question, what is it asking us to do? It wants us to maximize the profit. So we need to write an equation for the profit. That's going to be my objective. I'll call profit P, and we know profit is revenue minus cost, R minus C. And back in the previous section, section 8.3, we set up a profit function for this scenario. So I'm just going to remind us what that was. So the profit function here, let me zoom it out a little bit. The profit function here, remember, it was the revenue first. So the revenue was 20x plus 35y. And remember, that's coming from the fact that the X economy passengers, X is the quantity of economy passengers, and 20 is their ticket price. It's $2,000, which is $2,000. That's why I'm writing 20 here. So I'm writing 20 here instead of 2,000 because the question says that cost is measured, our cost function is measured in hundreds of dollars. And similarly, Y is the quantity of luxury passengers, and I'm multiplying it by 35 because that's the price that they pay for a ticket in hundreds of dollars, $3,500. Okay, and then I subtract my cost function, which will give us minus 1 over 40 x squared minus 1 over 15 xy minus 1 over 10 y squared minus 800. So that is our objective, the thing that we want to maximize or minimize. So there's another term called the constraint that I want to introduce. And that's why this is going to be called a constrained optimization problem. The constraint is an equation that's based off a restriction in the question. In fact, let's make this parentheses a bit bigger. So there's some other piece of information in this question that we can use to form an equation. And that's this bit where it says, suppose that they sell 340 tickets total. So we know that X is the number of economy tickets. Y is the number of luxury tickets. So if we add those together, that total should be 340. And that is our constraint equation. So nice. We want to find the max of the profit function subject to this constraint. X plus Y needs to be equal to 340. So we will do this in two ways. Method 1 we'll talk about in this video. And method 1 is called substitution. So substitution. So what we can do is we can use this, let me write it down, we can use the constraint to substitute into the objective. Okay, so if I isolate one of the variables in my constraint, and it looks like they're both pretty easy to isolate, so maybe I'll isolate y, and I get y equals 340 minus x, I can now plug that into the objective, and that'll get rid of one of the variables in the objective. So I'll get profit equals 20x plus 35y, but y is 340 minus x, minus 1/40th x squared, minus 1/15th times x, times y, which is 340 minus x, and then minus 1/10 y squared, where y is 340 minus x again, and then minus that 800 at the end. So the nice part about this is we've incorporated this constraint into our function by substituting it in, and we've eliminated one of the variables, which is nice because now we have one fewer variable. Okay, so let's simplify this a little bit. So we get 20x at the front, and if I distribute 35, we'll get plus 11,900 minus 35x minus 1/40 x squared. And if I distribute the minus 1/15th x in, this will become minus 68/3x after a little bit of cancellation with that fraction, and then plus 1/15 x squared. The next term I'll keep it as it is, minus 1/10 340 minus x squared minus 800. All right, so we have this profit function. It's looking long, but nonetheless, this is what we have. So we can simplify further by combining some like terms. So for example, I noticed that this is an x squared term, this is an x squared term. So I could get a common denominator. And it turns out that common denominator is 120. So if I multiply this first fraction top and bottom by 3, we'll get negative 3/120 x squared. And for the 1/15 x squared, I have to multiply the top and the bottom by 8. So that'll become plus 8/120 x squared. So combining those, we get p equals, let's write the x squared term first. So 8/20 minus 3/120 is going to be 5/120 x squared. And then we have the x term, so there's 20x, there's minus 35x, and there's the minus 68/3x. So I know 20x minus 35x, that's minus 15x. And then we have minus 68/3x. Then we get that minus 1/10 times 340 minus x quantity squared minus 100. So a little bit simplified, but still a number of terms here. So recall that if I want to find the max of a function like this is now in terms of one variable, we can do that using methods from the previous calc class. So for us, that was Math 30. Using Math 30 methods for finding maxes and mins. In our textbook, that was in section 5.1. So this point is actually a bit of a review from Math 30. The first thing that we'd need to do at this point, now that we have our function set up in terms of one variable, is we would need to find the critical points. To find the critical points. So that involves taking the derivative. So one thing that I can do to simplify this a little bit is 5 over 120 simplifies. That becomes 1 over 24. So the derivative of that first term, the 2 is going to come down, and 2 over 24 becomes 1 over 12. So we have 1 over 12x. Then we'll have minus 15 minus 68 over 3. And the reason why I didn't simplify this 340 minus x squared term before was it's easy to take the derivative of in this form. So I was just getting myself ready for that point. So I can do chain rule on this. The 2 comes down, and we'll get a minus 1/5 in front. And then that subtracts 1 from the power. So now that we get this whole thing to the 1, keep the inside the same, 340 minus x. But then we got to do chain rule and multiply by the derivative of the inside. Derivative of 340 minus x is negative 1. And then the derivative of the negative 800 would be 0. All right. So let's simplify further. We get p prime equals. Okay, so now to combine some of these terms, it's going to be helpful to start to get a common denominator. So negative 15, let's make the denominator 3 to match this next fraction. So negative 15 is the same thing as negative 45 over 3 if I get a common denominator. All right, so p prime equals, we have 1 over 12th x. And then we have minus 45 over 3 minus 68 over 3. And then when I distribute out the rest of this, we'll end up with plus 68 and then minus 1/5 x. Okay, so let's get some more common denominators. So 68 is a constant. Let's also make that denominator 3. 68 becomes 204 over 3 if you multiply the top and the bottom by 3. And then with both of the x terms, with the 1/12 x and the minus 1/5 x, that common denominator is going to be 60. So with the 1/12 x, I can multiply the top and the bottom by 5 and get that it's 5 over 60x. I can multiply negative 1 over 5x top and bottom by 12 to get negative 12 over 60x. Okay, so combining those x terms, we get 5 over 60x minus 12 over 60x. So that gives us negative 7 over 60x. And now if I combine all the constant terms that have this denominator of 3, we will end up with plus 91 over 3. Okay, so we have fractions still, but still this is a lot simpler than it used to be. It used to be pretty long. We had to do a fair bit of algebra to get it to this point. All right, so we're finding critical points. Next thing we need to do to get them is set our derivative equal to 0. All right, so let's set our derivative equal to 0. Ooh, let's write that S a little better. Set our derivative equal to 0. That gives us negative 7 over 60x plus 91 over 3 equals 0. If I rearrange this a bit, we get positive 7 over 60x equals 91 over 3. And now I can isolate x by multiplying both sides by 60 over 7 by the reciprocal. That gives us 91 over 3 times 60 over 7. And then we get some nice cancellation. 60 and 3 divides 60, and I'm left with a 1 on the bottom and a 20 on the top. And 7 also divides 91, and I'm left with 13 on the top and 1 on the bottom. So overall, I get 13 times 20, which is 260. So I know what x is. But remember that this question also wanted y. It wanted the combination of passengers. We just have the number of passengers associated with x. Okay, so we need to figure out y still. So remember y, the formula for that was we could use y was 340 minus x. That's coming from our constraint. So if I plug into this, we get y equals 340 minus the x value, which is 260. So y equals 80. So at this point, we know what x is, and we know what y is. Okay, so one quick comment that I want to make about this is, when I find critical points, technically I need to be finding where the derivative equals 0, and also where the derivative is undefined. In this class, we're not going to worry about the situations where the derivative is undefined and those critical points. So in our class, we won't worry about critical points where the derivative is undefined. We're just going to worry about the ones where the derivative is equal to 0. So in Math 30 or in the previous calculus class, that's something that we considered more. In our class, we're going to simplify the process a little bit there and only focus on the possibility where the derivative is 0. Okay, so we know we get this critical point when x is 260. But we don't know whether this corresponds to a max or a min. So we need to now test our critical point. We need to test our critical point. And we can do that, one of the ways we can do it is using the second derivative test. But this is the second derivative test for one variable functions. So let's recall how that worked. So we take our second derivative. So let's see, our first derivative was here. So if I take the derivative of that, we'll end up with just this -7/60. So that's a nice constant. So now I plug in my critical value, my critical number, which was x is 260. But there's no x to plug into here. So when I do plug it in, I just end up with -7/60. Okay, so that makes it easier actually. And this number is negative. And because it's negative, when I think about the graph, at this critical point where x is 260, at that critical point, our function needs to be concave down. So the fact that the second derivative is negative means that p is concave down. It's concave down at this critical point, and looking at the graph now, we can tell, oh, that means that there is a max at the critical point. So now we just write a sentence stating our conclusion. So by the second derivative test, the profit is maximized if the cruise sells 260, that needs to be X, so that's economy tickets, 260 economy tickets, and 80 for Y, that's the number of luxury tickets, and 80 luxury tickets. All right, so let's box our answer here. So that is our answer. Okay, so we saw optimization questions like this, max-min problems, in Math 30 in section 5.1, where I had this constraint equation. I had to use it to substitute into that objective, find critical points, and test them to see if they give us a max or a min. Okay, so I want to note one thing, which is just as in the previous section, 8.3, we're going to assume that the local extrema that we get from the second derivative test, because technically even this second derivative test for one variable functions is technically just testing for local mins and local maxes. We're going to assume that those local mins and local maxes that we get are actually absolute extrema, which is what we wanted in this problem. We wanted the absolute max profit. And it's possible to justify why this is, why the local max here is an absolute max. I just want to focus more on doing computations rather than that justification, so I'm not going to talk about that justification in this video. All right, so I want to end this video by talking about, well, what are the drawbacks or the cons of this method? Well, as we saw, this is algebra heavy, and the algebra can be tedious, especially in these situations where we have these longer functions and then we got to substitute into that longer function. So the algebra can be tedious when we do the substitution. So ideally, we would like a less tedious method. And we will talk about that in the next video. It's something called Lagrange multipliers. So in terms of our goals for this section, we have finished our first goal, which is talking about how to solve a constrained optimization problem, a max or min problem, using substitution.